Hello everyone. So I'm going to be talking about RAG, or Retrieval Augmented Generation, today. Who of you has already heard the term RAG before? Well, it's most of you. That's very cool. So who of you has already used RAG? Okay. Well, in products such as ChatGPT or in support chatbots, they all make use of RAG. So I would assume that all of you have already used RAG in some sort of way, or at least seen RAG in action. Is there anyone in the audience who has already built their own RAG system? Okay. Well, that's perfect then. So this is what this talk is going to be about. I'm going to take you to the steps of how you can build your own RAG system. And then I'm going to show you a few techniques that you can implement to make it even more capable. Now, this talk is going to be very technical. I'm going to be showing a lot of code, Python code specifically. I'm going to show a few examples. I'm going to show up 4 examples, and for each example, I'm going to start with the most basic version, and then I'm going to show a few techniques that we can apply to make it better. So, my name is Max. I've been in web development for, well, quite some time now, but recently I really enjoyed building with AI. So not just large language models, but also diffusion models. I'm based in Switzerland, and I would also be very happy to connect with as many of you as possible. If you want to do so, you can either follow me on Twitter or you can find me on LinkedIn. Just type in my name. So I'm an engineer at a company called Sutro, and at Sutro we are using large language models to enable everyone to build very quickly production-ready applications. And how that works is that you describe what kind of app you want, and we are building your initial version of the app for you in just 1 minute, and then from there you can go on. You can say, hey, I want those and those changes implemented. You can change the styling, all of that. And as soon as you're done and happy with the result, then you can publish the app for iOS, Android, the web, and everything. So if that sounds interesting to you, feel free to check out sutro.xyz. Feel free to sign up for a waitlist or just come find me after my talk. So, large language models. I think by now all of you have heard about large language models, probably used large language models too. All of the models that we are seeing today are based on the transformer architecture that was released or introduced by a research paper released in 2017, mostly by Google researchers, that was titled "Attention is All You Need." And large language models are amazing. They can do so much for us. They enable all kinds of new applications. But they also have a few downsides. So first of all, there is a knowledge cutoff date. All of those models have been trained up to a certain point in time. And if you want to ask them something about that happened since then, they will not know. And there's also a lot of information that will never make it into a large language model in the first place, which could be like very personal information, but it could also be like company internal information. And this is related to not having the knowledge, but if the model doesn't know an answer, it will not tell you so. It will just make up an answer. And basically, you can never really be sure if the answer is correct or not. Now, all of those problems are because the model doesn't really have access to the information that we need. Now, there are 2 ways on how we can teach new information to a large language model. That is fine-tuning or RAG. And so fine-tuning is kind of is like the process of continuing the training, basically, with your custom data. In practice, this proves to be very difficult, though, because large language models usually get trained in 2 stages. So in the first stage, they just ingest a lot of knowledge from like the internet. And when that is done, the model knows a lot basically, but it's not really usable because there is not really a good way of how you can interact with the model. And so in the second phase, we have the instruction fine-tuning phase. And in this, basically, the model is being taught how to interact with the user, like mostly in this chat style. And so if we want to fine-tune a model, then we have to do it in this like instruction fine-tuning way. So we have to break down all of our information in those question and answer pairs, which is kind of difficult to do. Also, fine-tuning uses a lot of resources and is expensive and slow. It's still not fully up to date because even if you do that like once a day or like every night, you do like fine-tuning of the model. If you get an email the next morning, you ask about that email in the afternoon, it will still not know about it, right? So it's never going to be fully up to date. And it also doesn't solve the hallucination problem. If you ask something that is not in your data, then it will just make up an answer. So we're using fine-tuning mostly if we want to teach a new behavior to a model. And we use RAG for, well, ad hoc knowledge retrieval. Now, how does a RAG system look like? Typically, it looks something like this. So you have your own data, it could be company internal data, from all kinds of sources. Could be from a database, could be like various unstructured documents, could be APIs. You want to gather all of them in like a central index. And then when the user asks a question, you first go to the index, you find all the relevant documents for this query, and then you would send like a system prompt plus the user's query plus the relevant data that you fetch from the index to the LLM, which then comes up with the answer that is based on the context. We are going to be using a framework called LlamaIndex in this talk. Now, LlamaIndex is like a data indexing framework. I think it's really cool. It enables us to do those things very quickly, but then again, it's not the only way of how we could build RAG applications. That being said, I'm not affiliated with LlamaIndex in any way. I just really enjoy using it. So one central part of building a RAG system is using embedding models. And what embedding models do is they take like human readable text and transform it into vectors, embedding vectors. So from a text, we just get a list of numbers basically. And those numbers, they are being generated by an embedding model, and they basically represent the words, or rather the tokens of the text in this world understanding of this embedding model. And well, there's a lot of embedding models out there, and I think it's really important that you do your research first and make sure you choose the right embedding model, because once you start indexing your files, then it gets really difficult to change the embedding model later, because you would have to recalculate all of the embeddings basically. I recently found a very cool article, which is linked below, and it was comparing a lot of different embedding models. And what I'm personally very interested in is the multilingual capabilities. You see, I work for an American company, so our correspondence is in English, but my native language is German, so I have a lot of documents in German as well. And yeah, I want to use a model that understands at least those 2 different languages. And here in this comparison, you can see there are the OpenAI embedding models, which you can use through their API. But there are other like open source models as well, the Mistral model, for example. And then there's a model called BGE-M3, which is from the Beijing Academy of AI, I think. And it proves to be like super capable, especially with in its like multilingual understanding. For a more up-to-date comparison between different embedding models, there is the Massive Text Embedding Benchmark Leaderboard by Hugging Face, where you have like basically all of the available embedding models, and you see how they compare to each other. Now, during this talk, I'm going to be working with the BGE-M3, especially because it's an open source model and I can run it locally, which I think is super cool. So let's start with a very first simple example. I want to build a Paul Graham bot. Paul Graham, that's this guy. So many years ago, he founded a company called ViaWeb and later sold it to Yahoo. And just a few years later, he went on to found Y Combinator, a startup accelerator who invested in like most of the tech unicorns that we see today. Now, Paul Graham also has a blog where he publishes essays about his thoughts, and there's a lot of wisdom in them, but it's a lot of content. So I want to build like a little chatbot that ingests all of those essays, and we can just ask it very specific questions. Now for this example, I want to use, I'm already using the open source embedding model, but I also want to use an open source AI model, LLM model. And for that, well, there's a few ways on how we can run those locally, but I would say the easiest way is with an application called Ollama. Now, Ollama, you could just install it in your computer, and you can pull any publicly available model and just run it. It also offers an API, and it's just super easy to use. So this is how we would build like an initial version of this Paul Graham bot. Super easy, right? So first we specify the embedding model. We say it should be the BGE-M3, and it will, the first time it will just pull this model from Hugging Face, and then it will run locally. For the LLM, we want to use the Ollama collector with the Llama 3 model, the 8B model from Llama 3. And that's a very small model though, but it's very capable for its size. And then to ingest all of the data that we have in like text files in a directory, we could just use a simple directory reader from Llama Index. So that's super easy. If we have the documents, we just create a new vector store index from those, and then we can use it as a query engine and ask it any questions, right? So that's super simple. There's just a few lines of code to build this. Now, there are a few ways on how we can make this a bit better, though. So first of all, one problem with that is that when we start it, then it's just going to index all of the documents. And basically, if we start it again, it has to index the documents again. So that doesn't really make sense. Let's try to at least persist those documents. That's very simple. We could just use the storage context of the index and say we want to persist it into a specific folder. And the next time we're loading it, we just say load the index from storage from this like specific directory that we saved it in. Then, well, the next step we could do is we don't want the whole document in one piece, right? If we send the whole document to the large language model, first of all, it's going to be slow. And second of all, it's going to be quite expensive because we're going to use a lot of tokens for that. So we want to split the text into smaller chunks, smaller nodes. And we can do that by specifying a transformation and using a token text splitter for that. So we can say, hey, our chunk size should be maximum 1024. It could, of course, be smaller or bigger too. And there should be like a chunk overlap of like 20 tokens. And so the next time we're running that, we just get like those small chunks that we send to the large language model, and it's going to be faster. Now, the standard retrieval method that is being used is one that's called top K. Top K just means like it takes like the top, however many you specify documents that are the most relevant. And of course, we can specify, hey, we want the top K 5, for example, the 5 matching chunks. But then we could also do like some post-processing of that, and we could say, hey, we got those chunks, but not all of them are like super relevant. So we could say, hey, we want the similarity cutoff of, in this case, 0.6. It could be any value from 0 to 1, basically. And then that's the response synthesizer is basically the part that prepares the prompt for the LLM. And there's a few different modes that we can use. For example, we could use the refine mode. It's going to start with the very first chunk that we received. It's going to build a response based on that, and then it's going to go through the others and refine its response, basically. And there are various modes that we could use here. So how does that look like? We could ask it, for example, what did the author do in his youth? And it would say, in his youth, the author worked on writing short stories and programming. And basically, it fetched all of this information from like a relevant essay. Okay, that was a super simple example. Let's do something a bit more relevant. So here at LambdaConf, I've seen there's like 84 speakers in total. There's 4 tracks at the same time. Plus, on the schedule, you only see the speaker and the, I think the talk title, but you don't really see the description of the talk. And so I thought it could be interesting if we build like some sort of index and we could ask it questions about the talks and the speakers here at the conference. Now, how we could do that is on the website of LambdaConf, there's this section called speakers. It has like a list of all the speakers. And if you click on a speaker, then it will show you the speaker's talks, including like the title, the description, and everything. So for that, I'm just going to prepare like a little bit, a little code to basically parse this speakers page. I will get all the links to the speakers, and then I'm going to prepare like a list of links of all the speakers. Now, what we have is a list of links to websites. And well, reading from a website is not something that Llama Index does by itself, but there is this portal called LlamaHub. And LlamaHub is awesome because there's all kinds of integrations that we can use with Llama Index. There's all kinds of data loaders from like all various sources. And there's one that we could use. It's called the Beautiful Soup web reader. So Beautiful Soup is like this HTML parsing Python library. And we could just say, hey, download this loader from LlamaHub. And then we have this Beautiful Soup web reader, which we're just going to provide with the list of the links that we prepared. And it gets us a list of documents back that we then can index. And that's it. Super simple, right? Now, if I look more into how those documents look like, they will look something like this. So this is from my speakers page. And as you can see, there's my name in there. Somewhere there's the title and there's a description as well, but there's a lot of overhead. That's because it basically took the whole content of the website as text. So we also have like the the whole navigation things. We have like the follow us, the hackathon, conference guide, whatsoever. So this is not that usable for us, I guess, because we're sending like a lot of overhead to the large language model. It might get confused. We're using up a lot of tokens. Isn't there a better way? And yes, there is. So Llama Index provides this OpenAI Pydantic program, it's called. And what it does is, from any document, basically, we have to provide a Pydantic schema, in this case for the speaker, who has a name, company name, and a list of talks. And because I saw that there are some speakers that give multiple talks, right? And so we can create this OpenAI Pydantic program. It will use the OpenAI function API to basically parse this raw document into this very specific format which we need. For that, we have to also provide like the prompt template, which says parse the following excerpt from a website about the speaker at the conference into the required object format. Then there's a placeholder for the input document, and then it says return the answer as a Pydantic object. The Pydantic schema is given below. And well, now I have like one function that takes all of those raw values and puts them into one document that we then could index. In there, we just have the speaker name, speaker company, talk title, and talk abstract. So we can use that here in our very custom ingestion pipeline, which we could use to ingest the data from those documents, those raw documents. And in this ingestion pipeline, we specify a few transformations. So first of all, we have this program extractor, which we just defined. That's the OpenAI Pydantic program. And then basically, I create a known transform component, which is super easy to do, which takes a list of those speakers and basically creates a list of talks, because we want to index every talk as its own document. So we have the program extractor, the presentation extractor. Then we're going to create the embeddings. In this case, we're using OpenAI for that. And then there's another cool thing which Llama Index provides. That's called the keyword extractor. And what it does, basically, it analyzes the content of the document, and it comes up with a few, like up to 10 keywords in this case, to use for that. And then, we just run it again, the pipeline with the raw documents. And this is the result. As you can see, it's much cleaner. It has less content in there. You have a few keywords, large language models, retrieval augmented generation, vector database, and so on and so on. And then we have the text, which is just the speaker name, speaker company, talk title, talk abstract, and that's it. That's all we need, basically. And so with this new clean index, we can use it to ask a few questions. I can ask, hey, what is Valentina talking about? And it will say, hey, Valentina is talking about her experience of building Storic, a platform to create personalized children's books and guiding the audience to 3 key stages of developing an AI-powered product. And that's right. That's how it was written on the website. But I could also ask it about, hey, who is talking about ballerina? And it will say, Samira Jayasoma is talking about ballerina. So that's very cool. I could also ask it, hey, there's a lot of talks about WebAssembly, for example. Who is talking about like which specific aspects of WebAssembly? Now let's go to the third example. This is something I wanted for a long time. My Gmail account is super messy. I have thousands of mails. I get a lot of mails every day. And it's very difficult to like find something in there. And I just want to build an index over that. And as it turns out, with Llama Index, it's just super easy. So I exported all of my emails basically into a folder, so in like the .eml format. And what I can do is I can just use the simple directory reader again, and that's it. Super, super simple. There's a few problems with that though. One of them is I saw that I'm not super happy with the way that those emails are parsed, especially when I'm asking it now, hey, when is my dentist appointment? Because I got an email from my dentist and they sent me a date, but the date was not in the email itself, but in a PDF attachment. And which is a weird way to send it, but okay. As it turns out, the simple directory reader doesn't really take care of attachments at all. And it also puts like all of the email headers into the metadata, which is kind of messy too. So anyway, it turns out you can just do those things manually too. You don't really need to read all of that, but what I did is I used a library called Fast Mail Parser, which I think was implemented in Rust originally and then ported to Python. It's super fast, super effective. I'm using that. I'm also going to parse all of the attachments and just attach all of the like PDF content into the same document. That's it. Now, so far, we've only used the vector star index from Llama index, which was good enough for those basic use cases. But for now, because we have a lot of data, let's use a real vector database. Now, in this case, I'm going to be using a vector database called ChromaDB. I like Chroma because it's open source, it's super easy to use, it's quite fast, you can run it locally. But there are many other solutions out there. There's like Pinecone, VV8. You could also store it in Postgres. There's many possibilities. Now to use it or to use it in a vector store like Chroma, we just create a new Chroma client. It's important that we use a persistent client for that because we don't want to have to reindex this all of the time. And then we create a new collection called Gmail in this case. We create a new vector store from this Chroma collection. And then the storage context is just going to use this vector store basically. Yeah, now in my custom email parser, I also set a few metadata. I set metadata for the sender of the email. I set metadata for the subject, the date when it was sent. So all of the information that is kind of relevant to me. And now I want to provide like some sort of info about how this data is structured. For that, I create the vector store info instance. I say, hey, this is a collection of my private emails from Gmail. I say the metadata contains a subject. I tell what kind of type it is. It contains the date. It contains the sender, and that's it, right? And what I want to use now is a thing called vector index auto retriever. So that's something that Llama index provides, and it's super cool. I think it makes a lot of sense. If I ask it a question, then it will first basically pre-process this prompt and come up with the filter of metadata to be used with the vector star. All it needs for that is basically this information about how the metadata is structured. And yeah, I think it's really cool that it is possible with so few lines of code. And now I could just ask it questions like, hey, what promotion did Uber send me in January? And what it will do first is it will create metadata filters for the sender that it includes Uber. It will limit the date to anything in January. And then it will basically find the right email and it say, hey, Uber sent an email with the 25% coupon code. And of course, I could also ask it then, hey, when is my dentist appointment? And because it has access to the parsed PDF file in there, It can tell me, hey, your dentist appointment is on Thursday, May 16th. So that was it for the third example. Let's look at another thing. I think this is very common, right? This is chat with the documentation. You see this a lot right now. And once again, thanks to Llama Index, thanks to Llama Hub, specifically, this is super easy to do. There is this GitHub client from Llama Hub that we can use to basically load any data from a GitHub repository. That could be issues, that could be code, it could be commits even, anything really. But we are specifically interested now in this Llama Index repository, and we want to filter the docs/docs directory because that's where they have all of their docs in the markdown format. We can have a filter for we only want the markdown files, the rest doesn't really interest us. And then we just, use the reader to load the data. We can even specify the branch that it should use. And then we get the list of documents, and that's it. Super easy. So how can we use this data now? Well, once again, we just use this index as a chat engine. We basically have to keep a list of chat messages that were sent, and then we just say chat engine.chat. Then we specify like the new question that the user had, and we pass in all of the chat history, and that's it. Now, I think there's a better way of how we could do that, and that's with like a conversational agent. Because what happens here now is every time a user asks something, the retriever basically first tries to get all of the relevant documentation. But for example, if the user asks something about, hey, I'm very interested in, I don't know, embedding models, for example, and then he has a follow-up question. And then for the follow-up question, I think all of the context might already be there. But our retriever engine comes up with the whole list of documents that are probably not really relevant then for this context. And so that's not really optimal. So in the conversational agent, basically what happens is the user just chats to an AI, and the AI basically has a tool to its disposal to search for relevant information. Now there's a way of how we could do that with the Llama Index too, but I just feel like Llama Index is very good at indexing data. It's not so good for building chatbots and stuff. So I'm going to be using LangChain for that, another framework. And so this is how it could be done. So we define a tool. We can use this add tool decorator here. It's just a search index tool. The parameter is going to be a query, a search query. It's going to retrieve all of the relevant nodes from our index, and it joins them all together into a big string. And then we create a new agent using the create OpenAI tools agent. So this is going to be using the OpenAI function calling API, which is super easy to use. For a prompt, we can just use one from the LangChain hub, but we could also, of course, specify our own. And we provided access to all of the tools it needs. We create a new agent executor. We invoke it with the input and the chat history and all of the context it needs. And now, if we ask it a question like, hey, how can I parse information from an image? Sorry, the question is actually wrong. It should be what kind of embedding models can I use with Llama Index? Then it will parse the documentation, basically query the documentation, parse all of the relevant documents, And then it will say, hey, Llama Index supports a variety of embedding models to represent your documents using sophisticated numerical representations. Here are the main categories and specific models supported, and it goes on and on and on of all the embedding models that are supported. Now, if we have this follow-up question like, hey, which of those can run locally, then it will realize that it already has all of the context because it was specified in the documents themselves, which can run locally and which can't. And it will just say, hey, Hugging Face embeddings can run locally, and that's it. So that's super cool. And yeah, I just showed you like a few examples now. There's obviously a lot of even more advanced techniques out there. If you want to learn about them, you can check out the Llama Index website. They have a lot of great guides. They have a lot of examples too. And yeah, that's it. Thank you very much. Are there questions?
I just wanted to understand better where the Llama thing was running. So you were doing the Python code, and was that all running on your local machine, and all the AI questions go into your machine, or was there like a cloud instance of AI? Because usually I go into the cloud and I type into ChatGPT, so I'm like, everything's running there. So I just wanted to know where things were running in your examples.
Yeah, that's a very good question. So those examples, like the Python code is all running locally. In all of my examples, I use the local embedding model, but I think only in the first example I used the local model, so that could run all offline basically. In the further examples, I mostly use the OpenAI model, so that's just the OpenAI API that is used there. Yeah.
So for like the speakers example, you generated the data for the speakers and what they were talking, and then did you upload that to like a ChatGPT model to then ask it the questions? Or that's what I'm confused about, is you generated the data, then you put it somewhere?
No, so the whole index with all of the embeddings, all of the data, that's all locally.
Okay.
And basically, I only fetch the relevant documents. I send those as context to the OpenAI API, basically.
Okay.
Yeah.
That was what I needed to know.
How do you deal with hallucinations?
So basically, you specify in the prompt, you can say, hey, only answer the questions based on the provided context. If the context doesn't really have anything on the question, then just say that you don't know. But that's usually, it's just handled by like Llama Index, who already does that for you. Yeah.
Thank you.
In one of the examples, you chunked the documents. One thing I couldn't tell was my understanding is that when you provided the question, it will limit the tokens sent to the model to the most relevant chunks that it found based on the question? Like, where does that happen?
Yeah, that's right. So because those documents are quite large, they get chunked up into like smaller parts. And I think usually you always want to do that unless you have like very small documents. So the vector retriever basically only finds the chunks that are, well, the most relevant for the user's question, and only those get sent to as context to the large language model. That being said, there's a lot of techniques that we could use in this case. For example, we could say, hey, maybe those small chunks, they might not contain enough information. So there's a technique called small to big, where you would still chunk up those documents, but if you send them to the LLM, you basically make them a little bit bigger than they were before. Yeah. So the LLM has a bit more context. Yeah. But there's a lot of like, yeah, fine-tuning that can be done with this. Yeah. And also there's like all kinds of chunking methods. So usually you will want to use something that is kind of some kind of chunking mechanism that is very specific to the data that you're dealing with. Right now we just used it to have like a text of a specific length. But for example, there's also like a chunking mechanism that we could use for like source code and specifically markdown files, and then you could chunk it in like all of the paragraphs, for example, or like all of the titles, stuff like that. Yeah.
That was kind of my question, so if I can ask a follow-on one to that one. So you've gone to the index, you've worked out the most appropriate chunks, you've retrieved those chunks and so on. When they're being sent over the network to the LLM, is that as plain text or are they compressed in a particular way? Or
no, so they are being sent as plain text, that's right, yeah.
Cool.
And yes, so maybe, I'm not sure if I really said that before, but I would say the cool thing about using a multilingual embedding model is that it kind of represents just the meaning of the words that you have. So even if the source document is like in German, you could still ask questions in English and it will find all of the relevant chunks, which I think is super, super useful.